Good afternoon, everybody. My name is Amanda Gilmet, and I took the role of manager this semester for our Apollo team. My team members include Isabel, Ryan, Rolando, Derek, and of course we had help from the second years as well. Sean knows what, sorry, nerves. And Tyler and Peter will be representing the second year group. So our mission statement is, we the class of 2015 are committed to improving the quality of society through patient care by utilizing our technical expertise, ensuring patient safety. So as you can see with our table of contents, we have our agenda for today. Each member of a group will be doing a section. Also on each of the slides, you'll see a red star in the left-hand corner, and that will be the section and the question number that we are answering. So just a quick introduction of the blood pressure. Blood pressure is a vital sign. Blood pressure is a pressure exerted by the blood circulating upon the walls of the blood vessels. What that means to us is, without blood pressure or the vital signs, it means no life. The blood pressure monitoring is a way to measure and monitor patients' blood pressure and able to diagnose certain conditions based on what they see. Now Isabel will be going over section A.
Good afternoon, everyone. My name is Isabel, and I'm going to go over our equipment description. But before I start with the description of the equipment, I'm going to go quickly through an introduction to the invasive blood pressure on a clinical perspective. So the invasive blood pressure technique measures the arterial pressure of the patient. It is a technique that is mostly used in ICU and in operating room. It provides a more accurate reading to the physician. It also provides an instant reading for the physician to diagnose the patient quickly. The IBP allows continuous reading of the blood pressure bit by bit from the patient. And then the introduction of the blood pressure on a biomedical engineering perspective. It is, this method required an insertion of a catheter through the artery of the patient. And then the catheter is connected to a sterile fluid system, and that is connected to an electronic monitor for the physician to read the waveform of the patient result after the blood pressure is done. Also, it provides a means of adding an open line to an artery. It's for injection of any medicine that is required. The description of our equipment. So when our team Apollo, when we designed our equipment, so patient welfare was the main priority. So we take patient factor really on our priority. So the design of the diaries and invasive blood pressure monitor include usability for the clinician, and then the unit is very user-friendly for clinician to measure patient invasive blood pressure. The unit is a real-time invasive arterial blood pressure channel. And also, I'd like to add from the previous slide, so the intent, the really intent application of the device is to take the signal of the faithfully reproduced result into a proper waveform for the physician to diagnose the patient properly. So the available function and feature that we have with our equipment here, so it allows physician to read the systolic and diastolic pressure. We have also static level of 0 millimeter mercury 40 millimeter, mercury 80 millimeter mercury, and 120 millimeter mercury. That would be demo lately with our presentation. And then, as you can see, at the front of our machine, we have specific indicators that is light up when pressed to be tested. And then we have push buttons. They are located at the front of the device for each specific function. And then we have also a display screen for the readout results. And then also we need to understand the usefulness of the value of the invasive blood pressure. So the invasive blood pressure usefulness is a real-time open line. The value of the invasive blood pressure provides to physicians the ability to directly view the invasive blood pressure and diagnose the problem in a real time. So what that means for the physician is that right away quickly, and then it's more efficient for them to diagnose the patient. And then it's able to see directly, so I just said that. And if there was a vascular shutdown, physician could see immediately what is wrong with the patient. So now we're going to call Sean Roswell for the section B.
I'm Sean Roswell. We're going to talk about the functional tests on our blood pressure device. So the first one is our zero calibration. This allows the clinician to turn a potentiometer in the front of the device to display static waveform as 0. This will tell them that the device is properly calibrated. The next video is a demo of this. So you can see the dynamic waveform displayed here. Then now the clinician will start to turn the potentiometer, and you can see it display the static waveform as 0. And then once you have verified this is correct, you can go back to displaying the dynamic waveform. So for the clinical perspective of this ensures to the clinician that the patient is hooked up correctly, that the value they're actually reading on the display is correct, and that the BP waveform we are looking at is on a calibrated scale. So to calibrate the device, you can either use an internal calibration system, or you can hook up a patient simulator like a PS420 and verify the waveform. So this is the demo of the patient simulator hooked up to our device. So it just displays the dynamic waveform, and you can see it's reproduced it faithfully from the PS420. So I'd like to ask Orlando to come present about the amplifier design.
Good afternoon, Orlando. We'll be talking about the amplifier design. So for the amplifier design, we chose the 8620, and the reason we chose this is because of its characteristics, which are similar to our BP waveform that we're trying to obtain. These characteristics include slew rate, CMR, frequency response. It's just any characteristics that would match the BP, we try to match it with the data sheet that we came up with the 8620. Okay, so for the signal, the most important thing that we're trying to capture with the 8620 was the dichotic notch here, right? So the 8620 is able to capture this quick transition here from the systolic to the diastolic. So that's why we chose that one with the slew rate and the fast response time. Because when there's signal, this happens very quickly. Okay, so of course with any biomedical instrument and device, we got noise. We got a problem with noise, and we got a problem with eliminating noise. So with this, with the 8620, the CMR, what it does is any input that's similar to the output, and or any input that's identical to the output, is neglected, and it's null by the 8620. Okay, so frequency response. Our 8620 is able to obtain a response of, or a frequency of up to 50 hertz, even though our signal coming in is only 3 hertz. And the reason for this is because between 3 hertz and 50 hertz, there's a lot of noise. But that noise is not just noise, it also carries medical value. And that's why we are to make sure that our instrumentation amplifier was able to capture that rate, or that range of noise. Okay, so from a clinical perspective, why the IA, why the instrumentation amplifier? The clinician or the nurse has to be absolutely faithful that the signal coming in from the patient is going to be reproduced accurately. That's with any linear gain that can happen at the output. The IA has to be able to track that signal. This is a dynamic signal, it's not a steady signal, or just one straight signal. So it has to be able to track it, whether it's high or low. And so by doing this, if the signal is precise and accurate, then the clinician and the nurse is able to properly diagnose and treat the patient. Like Paul Mandan, for session B.
So the internal calibration circuit. We have phase-mounted potentiometer for easy use to calibrate the signal to 0 millimeters per mercury. The screens are able to output the viewed signal, and the calibrated signal must work correctly so the patient's readings are accurate. The calibration must be done every 12 hours since the atmospheric pressure changes. We need to make sure that is always 0 in order to have the correct reading afterwards. So we incorporate troubleshooting aids. We have a test point at the output of the 8620 to view the unaltered signal. We also have a test point at the output of the peak and hold to ensure the screen is calibrated with the signal. We also have LEDs, with what we talked about later on. Test points allow us as technicians to easily see where the problem is. It's easier to go and see by the test point what the problem compared to looking at the huge device as one. So here's the peak and hold demo. So as you can see, the blue line here is the systolic, sorry. And then we have the diastolic. So we have the input at the systolic and then the output at systolic. So the slew rate is very fast, transitions from a gain to a sweep over time, as shown from Orlando talking about the cardiac notch. The waveform should not have any 90-degree transitions with it. It should be nice sweeps. Selectable static signals for output calibration. So we're able to switch from 0, 40, 80, and 120, as seen in the demo next. So we can see on the screen, it will show 0 millimeters per mercury as it reads. And we're able to switch it now up to 40, and it's in the plus or minus 3 millimeters per mercury range. We can switch it up to 80, and the final is 120. As you can see. So the clinical perspective, it gives confidence to the nurse to her ability to decrease the number of user errors, and also as well as being able to trust the device that the readings are correct, and able to recognize when the machine is not operating properly. Next
So I'm going to be talking about section E in your marking scheme, which is the readout function of the screen. Just change things up. We'll look over here a little bit. Everyone kind of focusing on that side. So on the left-hand side, we have our static level gain from 0, 40, 80, and 120. You can see that the output of the screen matches perfectly with 0, and then after a little peak, it comes back down to rough 40 and 41, so it's still within plus 3 millimeters of mercury for the calibration, as well as for 80, and as well as perfectly at 120 millimeters of mercury. And then, if you look over to the right video, we have our diastolic waveform with our peak and hold showing the systolic output. There's also an output at the diastolic, so the bottom of that waveform, which would be showing the 80 millimeters of mercury, as well as 120 millimeters of mercury, for our mean arterial pressure of 93, which is exactly where it should be to show for calibration. So what is our screen able to read out? We're able to read out the systolic, diastolic, and the map all on one screen. So it's all local, easy to see, and it displays all the information that is needed. To help troubleshoot for this, since the screen it's a programmable device that we use, so there could be lots of problems going wrong with it. And we'll have to decide if the problem's with the screen or is with the signal going into the screen. So the waveform is outputted to a digital screen. So there's an output just before, on the stack same, from the output to the screen, there's an output that we're able to attach to an oscilloscope just to see if that waveform is being portrayed properly. There's an LED on the PCB of our arterial blood pressure circuit, and that shows the pulse to show that it is matching up with the heart rate as well as the pulse showing on the screen, as well as there's LEDs on the PCB to show positive and negative 9 volts of speed supply to each. So first of all, what is systolic? It's the first rise of the arterial blood pressure waveform. It's your heart is pushing out blood, so that systolic pressure is the measurement of the amount of blood the heart is pushing out. And the diastolic is the second portion of that waveform, and that's the pressure that the arteries within the heart rest between beats. The mean pressure perfuses the body with blood allowing for circulation. So this means that perfusion is that the blood is being distributed throughout the body. Perfusion throughout the body has to be between on average, is between 60 and 70 millimeters of mercury. Without that, there's not proper perfusion, which means the blood is not reaching to your fingers and to your toes. So because of this, it's obviously the most important aspect of the arterial blood pressure waveform that we see, and that's why we're focusing so much on it. We'll pass things off to Pete to explain this game.
Okay, so essentially how we designed this screen. I have a 4 by 20 LCD screen that we're using for this project here. It has an adjustable contrast, so you can adjust how you view the output on the screen. So if it's too bright, too dim, you can adjust that for yourself. So we have everything able to be viewed, all the readings to be viewed in one local section with an extra loop for heart rate monitoring.
Which we'll show just after this.
And then the mean pressure, mean arterial pressure, it's been coded according to this equation right here. So diastolic times 2 plus systolic divided by 3. So this entire code, what I've used to write this code is I've used mainly if statements, while statements, constrain, mapping, analog read, digital read, constant integers, variable integers, and interrupt functions. And essentially, meets IT standards. So this is the message that we get on our heart rate monitor when we're testing. I've made it enabled, so you actually have to enable it to start your heart rate testing, because how this works is we use a 15-second time window to take the reading. And we count how many pulses are in that 15-second time window, multiply that by 4, which gives us our output of beats per minute. So this is a video just showing our example of 60 beats per minute. Yeah, so it reads out your heart rate, 60, and then the value it's measured in. And then we have our 100 beats per minute, so we increase the frequency on the pulses. And this is just showing that we get within 2% error of what we should be getting.
Which is within the 3 millimeters of mercury that we have to be within for calibration. Pass this off to Derek.
So I'm doing section F, simple quality upgrades. I'm Derek Dill, by the way. So the first thing I talk about is our circuit assembly. If the judges remember last semester when we presented ours, we had laid it all out in our box, just like in that picture. But if you see on the left side, I remember Dave actually asked, he said that we had spread it out and there's no room for our IBP. Well, we moved it all to the left side and then laid out our IBP now, so it has all the room to stay clear. To shield our circuits, we use fish paper again. It eliminates noise and keeps our circuits clean. We kept them organized, they're all separated, none of them are touching. Even the speaker is separate, and it eliminates all noise that will be caused by the circuits side by side. So our component layout. This is one of our boards. If you look, it's very clean soldering. The components aren't touching, they're far enough away that there would be no interference with them touching. We installed them very neatly, they're all done very professionally, and all our boards look like this. The criteria for our 3 test points. So when we thought of our test points, we thought of all the circuits we've built in all the years doing SIRE, electricity, CERT, and we thought that we would have test points that are a quick checkup, easy for the biomed. It's a clinical and biomedical engineering technology perspective, so for the clinician or the biomed, they're easy access, easy to see. Amanda talked about 3 of our test points, but they're LEDs. They're at the output of the 8620, they're at the input of the IC chips, and they were, it shows power going through. We have LEDs for you to be able to see, so it'd be easy to test our circuits. Special troubleshooting, as you saw from our circuits, they're small design, they're very basic, easy to understand for the biomed. We don't want anything that's too complicated. We all know what it's like to build these circuits in CAD. We want it to be very simple. We also included a separate board for a bridge rectifier to be able to tell where our power is going through. If there's any issues, we can connect it separately to test each circuit. Simple quality improvement, we had illuminated buttons on our machine. You can see that the ones that we have active are illuminated right now. These provide visual indicators that allow us to know which we're using at that moment. They're very clear. You guys can see them anywhere in the room. That's very... To protect against EMI, electrical magnetic interference, we have the noise-reduced shielding. We had that fish paper, like I said. See some right there, and there's in that picture we had before. So it protects our circuits. We also have them separate from each other, like I mentioned earlier, to avoid any noise or interference from other things. So I'd like to call up our second year representatives, Tyler Holdsworth and Peter.
Hello, my name is Tyler Holdsworth, and today I will be representing the second year BMEC Quality Upgrade and Circuit Incorporation Group. So I'm going to start off by going through the members of the group and some of the duties that they had. Me, I was the manager, and I was in charge of gathering a lot of technical information, getting it rolling. At the start, I had to select a team, devise the tasks to one another. I did so picking the different strengths and weaknesses from all the individuals, so hopefully we could all come together and have the best outcome. I also had a lot of the portion of the analog circuit design, and then we have Tommy Drampitic here. He was in charge of the Eagle computer automated design circuit, his printed circuit board, and the component layout. We have Peter Grandovich, who was just up there explaining how he did his microcontroller programming so that the information could be displayed on the LCD. We have Tim Regan. He also gave me a very big hand on making the analog circuit and constructing it. and he did the majority of the simulations that we threw into our BMEC report and gave it general assistance. Sean Mirza, he was in charge of a lot of the report formatting. He made it look nice, finalized a lot of things. He gave a really big hand with general assistance and the PowerPoints and also the operators and service manuals. Last but not least, we have Ian Tibbles. He was our big parts list guy, so he helped select the best components that we could use. So, if you'd like to go to the next slide. So, the specific design task we had was incorporating an analog systolic and diastolic detection circuit. We also had to do the microcontroller and Arduino ADC signal processor. This was all shown neatly and organized on the liquid crystal display. Also, as I said, the design on the Eagle CAD. We had to create the operator and service manuals, and for Rick's Biomedical Electronic Controls class, we had to process the report. So, the clinical significance is this waveform, as you can see right here. It's just the basic systolic here in your upper level, and your diastolic or valley, which is known as the peak. This is what the physicians need. However, they cannot just simply acquire that signal. They need the proper technological devices to interpret the pressure levels, give it to the voltage levels so that it can be easily read by them. So if you go to the next slide, I'll show you
Just to add a little bit onto that, sorry, the calibration that we've done here, so the peak, how we've set that up is that we have 0 volts, 1 volt, 2 volts, 3 volts, 4 volts, 5 volts. So our 1 volt correlates to 40 millimeters of mercury, 2 volts 80, 3 volts 120, 4 volts 160. And we consider anything above 160 to be 160 and above.
Okay, so here's the technical information. Due to the time restriction right now, as you can see, we have quite a few different op amps in here. We have some resistors, capacitors, diodes. As you see, these switches right here, unfortunately, we could not get CMOS components on Multisim because we could not locate them. So this is just a visual representation because you also can't get the transducer on Multisim too. So the ones that are open up there are normally open CMOS switches, and the ones here are normally closed. And they just basically function so that as this capacitor is slowly discharging, this one's fully charged, so they will both not be at 0 at the same time. So, go back to the story like that. So, and then as Peter was saying, there's the systolic that's represented at 120 millimeters of mercury, and that was at 3 volts, and that's coming out of the systolic out right here, which will go to the output meter. This valley here is actually the same signal that's being applied to here, but it's going through the inverting amplifier. So therefore, the systolic bottom actually becomes the peak, and that's what's out being interpreted as the 80 millimeters of mercury at 2 volts. So this all flows out of those two and goes into Peter's beautiful design of the Arduino and microcontroller.
Sure, we're going to call up Amanda and Derek. They'll give you the final parts of the presentation.
Alright, that includes our project. I would like to thank you for your time. It was a very interesting and hard project to complete. Of course, when anything you're supposed to have ready, it doesn't happen that day. So we're lucky enough to be able to have videos to show our work. Derek will go over the acknowledgements.
So as a group, we'd like to acknowledge Durham College and the efforts that those have contributed to the learning, teaching, and completion of our ECG and IBP monitor for our instrumentation class. This includes, but is not limited to, all outside sources that help troubleshoot any issues we may have had, the Durham College faculty that provided us with resources to complete the project, our peers at school were always quick to lend a hand, and most importantly, our professors that taught us everything that we know. Without the help of all these resources, we would not be able to complete our project. So most importantly, I'd like to acknowledge our teachers, no specific order: Rick, Sandra, Ravi, Rao, Pravin, Lauren, Tony, Dave, Louie, Phil, and Dave McKay. I'd also like to acknowledge the other teams. They're always very helpful. They never hesitated to give us a hand. So MedGen, ProMed, and Endeavor. We'd also like to acknowledge our second year team. We gave them a pretty big task. They never complained. They got it all complete in by the deadline that we had set for them. So Tyler, Ian, Tim, Sean, Peter, and Tommy, thank you guys, really appreciate it. And we'd like to acknowledge the graduating class from last year. I see some of you guys in the audience. So Genesis, Valence, Triforce, and Bioradicals. And the textbook that we had this year, the Introduction to Biomedical Equipment Technology, this textbook was a huge help when it came to providing us circuits, theory. It was invaluable when it came to doing our manuals. It provided us with so much information. We really needed the textbook. So, thanks. Bye.
Is there any questions?
Come up and, circuit.
Roll your